All right, so we're looking at simple harmonic equations from the equation booklet in IB, and we're also looking at why sine and cosine is such an important part of all of this. So sine and cosines are a way to describe simple harmonic motion. Please realize this is for one particle that's moving in simple harmonic motion that's part of some greater wave. But we're just looking at one particle. It could be going up and down, it could be going side to side, because it might be part of a transverse wave or it could be part of a longitudinal wave. But that one particle, as it vibrates back and forth, is obeying simple harmonic motion, which by definition means that its acceleration and displacement are always in opposite directions, but they are proportional in their magnitudes. So this oscillation is given an angular frequency, and we see that with this circle here. The idea is that we're going to go through 2 pi radians as the wave itself or the particle in the wave goes through one period t. So that's why we define angular velocity, which is the same thing as angular frequency, to be 2 pi radians over the period. And so the units here will be in radians per second. And that omega, that's not a W, that's an omega, and that omega is in radians per second. It's important that we use that because we're doing all these functions in radians, and so we're using omega as this angular frequency that enables these functions to work properly, so that as t goes from 0 to capital T, a period, if we think about what that means, one full period going through that time will allow the sine to go from 0 to 2 pi. And that's what omega is doing here. Notice if you plug in for small t, if you put in capital T, then omega, which is 2 pi over t, the capital T's would cancel and you would get 2 pi. So that would be one full sine oscillation, which is why we use omega here. Obviously, if t is 0, then it's interesting, small t is 0. Capital T is a constant. It has to do with the period here. We could time it. We could say, okay, go, 1001, 1002, 1003, 1004, stop. So, 4.5 seconds or something would be capital T. So it's never 0. Small t, if it's 0, means sine of 0 would be an initial case where it's going through the equilibrium point if we're using sine, or it's at one of the maximums if we're using cosine. So it's arbitrary whether we use sine or cosine. It's just when we decided to start the timing of the wave, of the particle, I should say, that's in the wave. Excellent. So we see here that A at any time, at any position displacement x, is proportional. And now we know the proportionality constant. We've always said, with simple harmonic motion, the acceleration is proportional to the displacement. But now we know that the proportionality constant is omega squared, which is very powerful because you know what omega is, 2 pi over t. So we know that the proportionality constant between A and x has to be 4 pi squared over t squared, which is very cool. The negative is obviously there because they're in opposite directions. Now, if we think about the velocity being the slope of the position, then clearly we're just offset by a 90-degree phase, because obviously when this thing is moving, and we know that at this point, for example, we had the position having a maximum slope would mean we'd have the velocity be at a maximum value. So that's why this happens. The extra omega out here has to be there for the units. So if you think about how the units work for velocity, we have to divide by time, and that omega provides that because the period is measured like whatever it is, 4.5, for example, seconds. So the omega has the proper units to make this x0 is in meters, and then omega is radians per second. And we end up with meters per second here. So very nice, because 2 pi radians, the radian idea, is there as well. So that's cool. And so if we take that one step farther, is where we come back to this equation, which is just continuing position, velocity, and then acceleration. They wanted to put this first so you understood what omega was and what omega related to A and x, but it would also be nice if this was after the velocity, so you can see the connection as these three go. Remember back to the very beginning of the year when we were doing lots of graphs where we'd have position, velocity, and acceleration graphs. All of those graphs need to go back into your mind right now and have those be appropriate, because that's what all of this is based on. Okay, so if we look at what V is here, and we recognize that V is going to change as we move over time, it makes sense that this V, if X is at 0, which would be the equilibrium, then this would disappear here, and we would get the maximum V, which would be V0. So they don't often put V0. Looks like maybe they never put V0. Yeah. So V0 would represent the maximum velocity, where X0 represents the maximum displacement, and A0 would represent the maximum acceleration, all of which happen at different points in the oscillation. And these equations get you that. So X is the displacement at a given moment. X0 is technically the amplitude of the displacement. It's the largest displacement you ever get, which obviously is the amplitude from the center line up to the maximum displacement. So that distance right there would be X0, where X itself is constantly changing. Okay, so that helps us understand this equation in order to get velocity at any time. And the most important being, I guess we should check with X was X0. So what happens when it's at the edge of its displacement and it's at maximum displacement? So now you get X0 squared minus X0 squared, which is 0, which makes sense because the velocity is 0 when it's turning around, and it turns around when X is at X0, which is to say when it's at its maximum displacement. So the plus minus is on here mostly because sometimes the velocity is going up, sometimes going down, so that's appropriate. Kinetic energy is given here. Please notice that the units work out nicely for energy, and that's because the omega is going to have a t squared in the denominator, and this is going to have meters squared, and so we end up with v squared, and so that's nice. And this is actually the kinetic energy at any time, but you can notice that if x is 0, because remember x is 0, the oscillator is going through the origin, through the equilibrium, and that means that the kinetic energy would be a maximum. So that's what they do to this next equation. They just say, okay, that's the total, what we would call the maximum kinetic energy. So the total energy is the maximum kinetic energy. And then if you ever want to know the potential energy, you're just going to take this equation minus this equation, and then you get the potential energy at any point. That's pretty cool. Now we have two specific problems where we actually figure out what's going on with omega and how this actually works according to things in the real world. So this is for a simple pendulum, which we did a lab on, that oscillates back and forth. When that pendulum is oscillating back and forth, the mass on the pendulum doesn't matter, neither does the amplitude, but the length of the pendulum does matter. So we get the square root of the L, that's an L there, and then divided by G, which is the acceleration due to gravity, or the gravity field. So on different planets, pendulums would act differently. But this will give you the period, and then once you knew this, you could plug that period in here, and you could know omega, and you could go about solving all sorts of things about that pendulum. Similarly for the mass on the spring, and it's interesting to think about where this equation with the t plugged in and how acceleration relates to x is how we can derive these equations, figuring out the forces involved. But that's in SOCOS. If you want to look at that, you can. It's not technically part of the curriculum. But understand what all of this means. Look for mass spring. Now the spring constant matters a lot, and whatever mass is hanging from the spring, or if it's horizontal, either way, that matters a lot. So another important thing here. So notice this gets you the period, but once you have the period, then you could do all these things related to simple harmonic motion and answer a very specific question. Well, that's what I'm down on the equations on 9.1. Hopefully that helped, and I'm going to sign off. Good luck, Stacey. Hope things are going well for you with this e-learning business, and see you online.